Today we've got a nice trig product that's going to utilize a pretty nice identity. And we're not just going to take advantage of the identity, but we will derive it. And in fact, we're going to derive it using complex numbers, in particular, Euler's complex exponential formula. And so we're trying to get kind of the most bang for our buck out of this, fairly simple problem. Okay, so what we want to see here is the value of the tangent of 1 degree times the tangent of 2 degrees times the tangent of 3 degrees, all the way ending at the tangent of 89 degrees. So maybe the first thing that I'd like to notice is that there's a natural pairing with each of these terms at the beginning with some terms at the end. So we can think about this as folding about the tangent of 45 degrees so that we're putting tangent of 1 degree next to tangent of 89 degrees and so on and so forth. So, like I pointed out, I'm going to recommute everything so that I have tangent of 1 degree times tangent of 89 degrees times tangent of 2 degrees times tangent of 88 degrees. And then that's going to go all the way up to the tangent of 44 degrees times the tangent of 46 degrees. And then we've got one thing which is left over on its own, and that's the tangent of 45 degrees. But the tangent of 45 degrees has a well-known value of 1. And you can in fact visualize that quite easily just by thinking about what type of right triangle has the property that the height is the same thing as the base. And that would be one with a 45-degree angle. In other words, an isosceles right triangle. So we don't even really need to include the tangent of 45 degrees. Okay. But now let's notice that each of these are of the form tangent of something times tangent of 90 degrees minus something. So we've got 89 is the same thing as 90 minus 1. We have 88 is the same thing as 90 minus 2. And finally, out here we have 46 is the same thing as 90 minus 44. Okay. And so that maybe motivates the need for the following type of formula. What is the tangent of theta times the tangent of 90 degrees minus theta? But I'm going to use radians at this point because it'll be easier when we swap everything into complex arithmetic. So I'll write this as pi over 2 radians minus theta. Okay, so now over here on the side, before we derive this, what I'd like to do is recall Euler's formula. So Euler has a lot of formulas, but this one is related to the complex exponential. And what it does is it says that e to the I theta is the same thing as cosine of theta plus I times sine of theta. But notice that means that e to the minus I theta is cosine of negative theta, which is the same thing as cosine of theta because cosine is even, plus I sine negative theta, but sine is odd, so we can bring that minus sign out. So we've got e to the I theta, e to the minus I theta. And now we can add and subtract these to get equations for cosine and sine in terms of these complex exponentials. And I'll leave the details out, but what we have is cosine of theta is the same thing as 1/2 and then e to the I theta plus e to the minus I theta. Whereas sine of theta is equal to 1 over 2I e to the I theta minus e to the minus I theta. Okay, nice. So those are the complex exponential versions of cosine theta and sine theta. But notice we can easily use these to get a complex exponential formula for tangent. So let's write that down here. So we have tangent of theta ends up being, well, it's sine over cosine. So part of the halves will cancel. Well, the whole half will cancel. We'll be left with a 1 over I. And then we'll have e to the I theta minus e to the minus I theta over e to the I theta plus e to the minus I theta. So there's a nice complex exponential version of the tangent function. So now we'll take this exponential version of tangent of theta along with the exponential version of tangent of pi over 2 minus theta and see what simplifies. First off, let's notice that both of them will have a factor of 1 over I. So if you take 1 over I times 1 over I, you get 1 over I squared or negative 1. So I'll take a minus sign out of the whole thing and then just focus on the rest. So I'll have e to the I theta minus e to the minus I theta over e to the I theta plus e to the minus I theta. So that's from my tangent of theta part. Now let's see what I have for the tangent of pi over 2 minus theta. So I'll have e to the I pi over 2 minus theta minus e to the minus I pi over 2 minus theta. Okay, so that's happening in the numerator, and then happening in the denominator, I'll have e to the I pi halves minus theta plus e to the minus I pi halves minus theta. And now in order to start the path of simplification, I'll take this second term in the product and I'll multiply it by a nice version of 1. And that nice version of 1 will be e to the I pi over 2 over e to the I pi over 2. So let's just indicate in this orange box that we're multiplying that orange overlined thing by this version of 1. Okay, so just bringing some stuff down, we'll have minus e to the I theta minus e to the minus I theta over e to the I theta plus e to the minus I theta. So that's this term. Then let's see what happens when we multiply this stuff through. That'll leave us with e to the I pi times e to the minus I theta for this first term. Really it's e to the I pi minus theta, but I'll use exponent rules to break that into two pieces. Okay, and then when we multiply the second term in the numerator by this, the pi over 2 stuff cancels, and we'll be left with minus e to the I theta. Okay, then let's see what we have in the denominator. So we'll have e to the I pi times e to the minus I theta, and then plus e to the I theta for the same type of reason. And now we use the fact that e to the I pi is negative 1. That's like one of the most famous formulas on the internet, so hopefully everyone is aware of this beautiful formula. So let's make those replacements. We still have this minus sign out front, and then we'll have e to the I theta minus e to the minus I theta. This is all happening over e to the I theta plus e to the minus I theta. And then this turns into minus e to the minus I theta minus e to the I theta over, let's see, minus e to the minus I theta plus e to the I theta. Okay, so now let's see if we can do some simplification, and we can do some nice simplification. Notice the numerator here is exactly the same as the denominator there, so we can cancel those out. And then the numerator here is almost the same as the denominator here. In fact, if we take this minus sign and move it through, we'll cancel each of these to plus signs, and then in fact, yes, these numerators match, which means they cancel out. So everything cancels out and we'll end up with the number 1. But now this is true for any theta, and this is exactly the setup we have for all of these up here. This would be like theta equal 1 degree, this would be like theta equals 2 degrees, and so on and so forth. So that means this product here is 1, this product here is 1, all the way up, all of those products are equal to 1, which of course gives us a value of 1, and that's a good place to stop. Thanks for watching and sticking around until the end of the video. And since you're here, don't forget to gently press that like button, subscribe, ring the bell, and select all notifications to never miss a video. If you want to get your name in the credits like you see here, access the live seminar series, review videos before release, and more, go to patreon.com/michaelpennmath and become a Patreon member today. If you want full ad-free course content, subscribe to my second channel, Math Major. I've got courses on linear algebra, complex analysis, and proofwriting, among several others. And that's everything. Bye.